previously in the lecture 1, we had discussed about the difference between kinematic synthesis as well as kinematic analysis. So kinematic synthesis deals with creation of a new mechanism according to a set of specifications or a new idea that is conceived by a person. Whereas kinematic analysis is analyzing or finding out the displacement, velocity, and acceleration for an already existing mechanism or an already designed mechanism. The basic difference between a kinematic synthesis and kinematic analysis. So we were able to differentiate that, and also we were able to list out, or we were able to classify the three different types of kinematic analysis. The first one is the type synthesis. In the type synthesis, we can figure out, or we can choose what kind of a mechanism we want to employ for the mechanisms that I want to design. So should I choose a lower pair mechanism, or should I choose a higher pair mechanism? Should it be a belt drive? Should it be a gear drive? That decision we should be able to take at the type synthesis level. So this becomes the first phase of the kinematic synthesis. And the second phase is the number synthesis. In the number synthesis, I am supposed to find out how many links are required for smooth functioning of the mechanisms. That smooth functioning can be identified through the degrees of freedom, which we can find out through the Grubler's criteria that we have discussed. Should it be 1 or more than 1? If the degree of freedom is equal to 0, system is a locked system, a locked mechanism which cannot move. So number synthesis, or the number of links, should be such that the degrees of freedom should be equal to 1 or more than 1 according to our desire. So this forms the second phase of the kinematic synthesis. The third and the last phase of the kinematic synthesis is the dimensional synthesis. I know the type of mechanisms, I know the number of links. What should be the dimension of the links is what I am supposed to find through the dimensional synthesis, and this forms the third phase of the kinematic synthesis. Right? Again, the dimensional synthesis can be classified into three different types. The first one is the motion generation. In the motion generation, I am interested in the motion of a particular link, right, which generates the path. Let me say link number 3 is generating a path. What are the different configurations or the positions that are taken up by the link 3 for producing a particular path? Right, that is what I am interested in. So that is called as motion generation, right? And again, there is something called as a path generation, another classification of dimensional synthesis. Generation, I am just interested in the path traced by a point on a link that is moving. So let me say I want to trace the path. I want to know what is a path that is traced by a point on link 3. I am interested only in the path generated. So that is called as the path generation. And the last type of dimensional synthesis is the function generation. In the function generation, both input link as well as the output link will be related to each other. If input moves by 10 degree, the output moves by 20 degree. They can be related by the equation y is equal to 2x. Right? So input is x, output is y. So y will be 2 times x. Right? So for a particular range, that is called as function generation, where there will be a relationship between an input link which is powered and output link which follows the input link. Whereas in the motion generation as well as the path generation, there will be no such relationship between the input and the output link. So in the function generation, you have to remember that input link and output link are related through a function. Y is equal to f of x. That is what we have to remember. Now we will start with the dimensional synthesis. Let me know that I know the type of mechanisms that is given to me. Let me say it should be a 4-bar mechanism or a slider crank mechanism. And of course, I know the number of links that are given in a system. I know that. That's not an issue. So now to find the dimensional synthesis using the 4-bar mechanism, or to find the dimensional synthesis for using the function generation for a 4-bar mechanism, right? That means I should be able to find the links or the dimensions of all the 4 links in a 4-bar mechanism. Right? For that, we have a equation called as Frontstand equation. So Frontstand equation is a very simple equation through which I can find out the link lengths, that is length of link 1, link 2, link 3, link 4 in a 4-bar mechanism. 4-bar mechanism has 4 links. So Frontstand equation should assist me, or it should guide me to find the dimension of all these 4 links. As simple as that. So what is Frontstand equation? It tells me how to design a 4-bar mechanism or a slider crank mechanism. It is applicable to both for function generation. If a specific function is given to me, y is equal to f of x, how to design a 4-bar mechanism, or how to identify lengths of all the links that are involved. That is the basic idea of the Frontstand equation. So it is named after its discoverer, Ferdinand Frontstand, right, who is an mechanism designer, basically from the United States. Right? So his equation is one of the most useful and easy to use tools for designing a function generating, right, a mechanism where input link is or output link is dependent on motion of the input link, right? So how to determine the link length in such a case is what the Frontstand equation tells me. So now let us go ahead, right, and find the Frontstand equation for a 4-bar mechanism, right? So first I will consider a 4-bar mechanism like this. So I have link 1, right, which is a fixed link, which are shown at 2 levels. So this is a link 2, which will be called as a crank, which will be powered through a motor. So I will call this as input link. So link 3 is a coupler which connects 2 and 4. So 4 either can be a rocker or it can be a crank. So let me say inclination of link 2 with respect to horizontal is theta 2, and inclination of link 4 with respect to horizontal is theta 4. I should be able to write the vectorial representation for the configuration that is shown. So that I have shown here. So for showing the vectorial representation, I should know how the angles are measured, right? So for that, let me say point A. So let me consider this as a reference. I am going to draw a horizontal line to the right side as shown. So this becomes the reference line for measurement of all angles. So theta 1 exists along the same line, right? So it does not exist anywhere. So angle exists in the same direction. So here I have shown the same direction. This will be the direction of vector for the link 1. So to find the direction of vector for the link 2, so this is the reference line that I already have because it is measured with respect to the horizontal. So I am going to measure the angle in the anti-clockwise direction. So in the same direction, I am going to represent the vector or the direction of the vector for 2. So that is shown as R2 here. This is the direction that is shown. So for 3, so this is point B is considered as a reference. A horizontal line is drawn to the right side. You can take anything as your reference. So angle is measured in the counterclockwise direction, and in the same direction I am going to represent the direction of vector for the link 3, and I have represented it as R3, that is shown here. So for R4, instead of measuring from C, I have taken the reference as D. I have drawn a right side horizontal line to the right side, and the angle theta 4 is measured in the counterclockwise direction. So in the same direction, I am going to show the direction of vector for the link 4 as R4, that is shown here. Right? So now if you observe, R2 and R3 are in the same direction, whereas R1 and R4 are in the exactly opposite direction. So I will consider R2 and R3 as positive and R1 and R4 as negative. So we have something called as a vector loop closure equation. So I can add all the vectors, that sum should be equal to 0. So R2 plus R3 minus R4 minus R1 should be equal to 0. This is called as a loop closure equation for the 4-bar mechanism that is shown in the figure. So this loop closure equation or the vector loop closure equation will be taken as a reference for the further level. So each vector R1, R2, R3, R4 represents vector for each link. Each link is represented as a vector. Each link has both magnitude as well as direction, right? So R1 has magnitude as well as direction. So similarly R2, R3, R4, they have both magnitude as well as the direction. So that will be represented through a complex polar form. So now I will borrow the same equation number 1 from the previous slide. So I write the same equation number 1 using the complex polar form. So R2 has both magnitude as well as direction. So small r2 represents the magnitude and theta 2 represents the direction. So similarly for r3 theta 3, r4 theta 4, r1 theta 1. The r1 represents the magnitude of the link 1, length of link 1. Theta 1 represents the angular position of link 1. So I have both the magnitude as well as direction for all the links represented in the form of a vector. R2 is a vector which has both magnitude, that is R2, and direction, that is theta 2. Direction here is nothing but the angular position, that is what we have. So now I know the Euler's equation from the trigonometry where I can write e to the power of j theta as cos theta plus or minus j sin theta. So wherever I find e to the power of j theta here, I am going to replace it by cos theta plus j sin theta. So let us do that exercise in the next slide. So I had r2 e to the power of j theta 2. So that has been replaced by cos 2 plus j sin theta 2. So similarly, wherever I had e to the power of j theta 3, that has been replaced by cos theta 3 plus j sin theta 3. So similarly for r4, so we have called it as cos theta 4 plus j sin theta 4. E to the power of j theta 4 is represented as cos theta 4 plus j sin theta 4 minus cos theta 1 plus j sin theta 1. Since theta 1 is equal to 0, that has been neglected. Right. So now let me compare the real and imaginary parts from the above. If a function if it has a coefficient of j, it becomes an imaginary part. If it has no coefficient of j, it becomes the real part. So in the above one, r2 cos theta 2 becomes the real part, r3 cos theta 3 becomes the real part, minus r4 cos theta 4 becomes the real part, minus r1 becomes the real part. So 0 is there, so obviously it will be available for both real as well as imaginary. So r1, it has only the real part, it has no imaginary component, so therefore it will be treated only for the real part. So r1 has no imaginary component. r2 j sin theta 2, so coefficient of j is r2 sin theta 2. So similarly we have written it for r3 and r4. So equation 2 and equation 3 represents the real and imaginary part for the equation or the vector loop closure equation, which has been expanded using the Euler's formula as shown. So now my next step is to simplify these things. How to simplify? What is my objective? My aim is to establish the relationship between theta 2 and theta 4. Theta 2 is the input link, theta 4 is the output link, right? So as determined by the limit line, right? So now through this expression or the expression that I am going to derive at the final one, I should be able to find out R1, R2, R3 and R4. Those values of R1, R2, R3, R4, through that I should be able to find out the relationship between theta 2 and theta 4 to satisfy the function y is equal to f of x. So I require only theta 2 and theta 4. Theta 3 is not required here. So my objective is to eliminate theta 3 from equation 2 and equation 3. So how to do that? Let's go back to the next slide. So here, so I have taken the same equations, equation 2 and equation 3. So now to eliminate theta 3, the one thing is segregate, bring the theta 3 terms to the left hand side, so that if they are squared and added, cos square theta 3 plus sin square theta 3, so theta 3 gets eliminated. So through that logical thinking, I have brought the theta 3 terms to the left hand side. So this is where I had the theta 3 terms, r3 cos theta 3 and r3 sin theta 3. Both have been brought to the left hand side and all other terms have been moved to the right hand side where there was 0. So there has been a sign change. Plus r2 cos theta 2 has become minus r2 cos theta 2, minus r4 cos theta 4 has become plus r4 cos theta 4, minus r1 has become plus r1. Similarly, equation 2 has become equation 4, equation 3 has been converted into equation 5. What is the next step? So let us take equation 4, equation 5. Now to eliminate theta 3, square both sides, LHS as well as RHS, and add them, so that theta 3 gets eliminated. So square both sides, you have to be careful because I am supposed to whole square them. I cannot individually square. So R3 cos theta 3 whole square will be equal to whole square of the right hand square, right hand term. So similarly do it for equation 4 and equation 5. So equation 6 is nothing but the resulting equation from 4, which is squared on both sides. So equation number 7 is nothing but equation 5, which is squared on both sides. So here you have to remember here. So this is, there are three terms involved here: r2 cos theta 2, r4 cos 4 and r1. So r2 cos theta 2 is considered as A, r4 cos theta 4 is considered as B, and r1 is considered as C. So again, here I have two terms. R2 sin theta 2, it is considered as A, and R4 sin theta 4, it is considered as B. So the first equation, that is equation 6, can be treated as A plus B plus C whole square. So I know the formula for both. A plus B plus C whole square is nothing but A square plus B square plus C square plus 2AB plus 2BC plus 2CA A square plus B square is a well-known formula. So I have to expand equation 6 and equation 7 according to the formulas that have been given here. So in a simple sense, let me go forward and expand them. So this is the equation 6 and equation 7 we have from the previous slide. So using the formula of A square plus B square R1. So R2 cos theta 2 is considered as A, R4 cos theta 4 is considered as B, and R1 is considered as C. So again, here I have two terms, R2 sin theta 2, it is considered as A, and R4 sin theta B square plus C square plus 2AB plus 2BC plus 2CA. A square plus B square is a well-known formula. So I have to expand equation 6 and equation 7 according to the formulas that have been given here. So in a simple sense, let me go forward and expand them. So this is the equation 6 and equation 7 we have from the previous slide. So using the formula of A square plus B square plus C, A plus B plus C whole square. So R2 cos theta 2 is the A term, that is A square plus B square plus C square. C square is only R square minus, so minus is because A is minus 2AB plus 2BC plus 2CA. So similarly, A plus B, A square plus B square minus, because A is plus 2AB. So since it is A has a negative coefficient, this has become the one. So equation 6 has become equation 8 after expansion. Equation 7 has become equation 9 after expansion. So take equation 8 and equation 9 and add them. Right. So when you add, you have cos square theta 3 and sin square theta 3. Cos square theta 3 and sin square theta 3 is 1. Therefore, the term theta 3 gets eliminated. All other resulting terms you can write. So similarly, you can observe here cos square theta 2 sin square theta 2. So this term gets eliminated. So for R4, you have cos square theta 4 plus sin square theta 4. So that also gets eliminated. Simplify all other terms. So R square, so this is what I have, R to the R4 square, this is what I have, plus R1 square. So all the remaining terms, just rewrite them as it is. Minus 2 R2 R4 cos theta 2 cos theta 4 I have written is as it is, plus 2 R4 R1 cos theta 4 I have written it as it is, minus 2 R1 R2 cos theta 2 written as it is. Right. So again, minus 2 R2 R4 sin theta 2 sin theta 4. All the terms have been written, they have been written, added as it is. Right, and they have been, the resultant equation has been called as equation number 10. So now equation 10 is of more importance to me. I will carry forward that to the next step, that is the equation 10. Right. So now I have to rearrange the equation 10, because now I have to clearly remember my objective is to find R1, R2, R3 and R4. So all the square terms, right, so they have been taken to the other side, so which has coefficient of only cos theta 4 and cos theta 2. If they have a cos theta 2 and cos theta 4, they have been shifted to the right hand side. If they are a combination of both theta 2 as well as theta 4, so all the other terms have been moved on to the left hand side. So now I have to eliminate, so only theta 2 and theta 4 has to remain to me. So there is the coefficient of both are R2 R4 and R2 R4. So now my objective is to eliminate that coefficient of cos theta 2 cos theta 4 sin theta 2 sin theta 4. Right. So because I know that cos theta 2 cos theta 4 plus sin theta 2 sin theta 4 will give me some trigonometric equation. So I don't want 2 R2 R4 to disturb me. So I want to eliminate that. So what I do is I divide both LHS as well as RHS by 2 R2 R4. So after doing that, so the resulting equation has been shown as equation number 12. So R2 square R4 square plus R1 square minus R3 square, the entire thing is divided by 2 R2 R4. So 2 R4 R1 by cos theta 4. So here R4 gets cancelled. So you get 2 R1, so 2 also gets cancelled. So R1 by R2 cos theta 4. So here R2 gets cancelled. So you get R1 by R4 cos theta 2. So you get only cos theta 2 cos theta 4 plus sin theta 2 sin theta 4. So now I get the same equation 12 to the next slide. So if you observe here, it results in this can be simplified using a trigonometric relation, cos A minus B. Cos A cos B plus sin A sin B is nothing but cos A minus B. So I know that equation. So all the resulting things. So let me call R1 by R4. Wherever there is R1 by R4. So instead of always calling it as R1 by R4, I am going to call it as K1. So similarly, wherever there is R1 by R2, instead of every time calling it as R1 by R2, I am going to simply call it as K2. So this entire thing, R2 square plus R4 square plus R1 square minus R3 square divided by 2 R2 R4. This entire thing I am going to call it as K3. right? And this entire right hand side can be written as cos A minus B, that is cos theta 2 minus theta 4. So the resulting equation can be written like this. So the first term, it simply becomes K3. So this term becomes this becomes K, this is nothing but K3. So this is nothing but K2 and this is nothing but K1. So this is K3 written as it is, K2 cos theta 4 minus K1 cos theta 2 equal to cos theta 2 minus theta 4. So now if you observe carefully, so I have the relationship between theta 2 and theta 4 represented in terms of the link lengths R1, R2. So K3, K1, K2, K3 are nothing but R1, R2, R3, R4, which are nothing but the link lengths. So this equation that we have obtained is called as the Frontstand equation for the 4-bar mechanism. By employing this mechanism, right, I can find out the link lengths, right, R1, R2, R3, R4. The length of the link will be such that they are going to satisfy the function that you have. Let me say y is equal to x square. Output should be square of the input, right? So for to produce that function or to generate that function, what should be the length of links is what the Frontstand equation tells me. It is as simple as that. So this is what you have to derive and show in the examination if they ask you to derive a Frontstand equation for a 4-bar mechanism. Right? So what was the objective of the derivation? So I wanted to establish the relationship between input rotation angle theta 2 and output rotation angle theta 4 as found out or as determined, which will be determined from the link lengths R1 to R4, R1, R2, R3 as well as a R4. So in the function generation via Frontstand equation, the idea is to determine R1, R2, R3, R4, which results in a summation of theta 2 minus theta 4, right? And that should produce the function that I want to generate, right? Something like y is equal to x square, right? So this will be the Frontstand equation K3 plus K2 cos theta 4 minus K1 cos theta 2 equal to cos theta 2 minus theta 4, where K1 will be R1 by R4, K2 will be R1 by R2, and K3 will be R2 square plus R4 square plus R1 square minus R3 square divided by 2R2 R4. So as simple as that. So, and one thing that we have to notice, so whenever we want to solve numerical problems, so instead of taking input angle as theta 2 and output angle as theta 4, so I will choose the input angle as theta and output angle as phi. So only thing that are going to change with respect to the previous slide is wherever there is theta 4, I am going to replace it by phi. I'm simply going to replace it by theta, right? So this is a note to consider for solving the numerical problems in the future, right? So the previous expression can be written as wherever there was theta 4 that has been replaced by phi, and wherever there is theta 2 that has been replaced by theta, right? So that is how I can rewrite the Frontstand equation if the input angle is theta and the output angle is phi. So now I have 4 link lengths here, R1, R2, R3, R4. This is what I am supposed to find through the Frontstand equation for a function that is given to me. So that particular length of R1, R2, R3, R4 that I am going to find using the Frontstand equation will help me to generate the function that is given to me. So that is what the Frontstand has conveyed through this derivation. In the next lecture, we will consider, we will find out how to derive these set of equations for a slider crank mechanism. Right? So this ends lecture number 2. Right?
As mentioned here, R1, R2, R3, and R4, we are used small a, small b, small c, and small a. Okay. In place of R1, it is called as a small a. In place of R2, it is called as a small b. In place of R3, it is called as small c. And in place of R4, it is considered as a small b. Where capital AB, it is one link, it is equal to small a. Capital BC, it is equal to small b. Capital CD, the link, it is called as a small c. And capital AD, it is equal to small a. Okay. That kind of example we are solved in the next lecture. Okay. Stay safe.